Starting us off is Russ Bowers from the University of Florida. And of course, Russ barely needs an introduction, but for the students in the audience, Russ is of course the Bowers of Bowers and Whitekamp, whose seminal work helped usher in the era of Parahydrogen enhanced magnetic resonance, and the reason that we're all here. So Russ's talk is going to be entitled Hyperpolarization from Parahydrogen Utilizing Intermetallic Nanoparticles. So with that, Russ, go ahead and take it away.
Thanks a lot, Boyd, for the introduction. Really delighted to participate in this inaugural PERM meeting. And I have to say that the organizers have really done a wonderful job at organizing this exciting meeting. Yeah, let's see. There we go. I want to acknowledge my research group, my current research group, and several of the former group members, in particular Evan Zhao, whose work I'll be presenting today. But none of this work would have been possible without the really exciting and dynamic collaborations that we've been able to develop with Professor Helena Hagelin-Weaver's group in the UF Chemical Engineering Department, and Professor Wenyu Wang and his group at Iowa State University Department of Chemistry and Ames Lab. I want to just let you know about a work that we're doing here in the National High Magnetic Field Lab to develop a user facilities for parahydrogen research. That includes converter technology, reactor systems, storage, and integration into the National High Magnetic Field Lab for parahydrogen research at fields up to 35 Tesla. Now, as Boyd mentioned, I've been involved in parahydrogen enhanced NMR research since the very beginning. And you can see here photos are from a news article that came out in the Caltech newsletter. That was shortly after the Challenger shuttle disaster, where the commission was formed to investigate that with Richard Feynman. And at about the same time, in the same issue, they presented an article about our recent results that had been published in these two articles that you may have cited, or probably have cited if you're working in parahydrogen related research. And but you know, after graduation, I left the field to pursue other forms of hyperpolarization. And it wasn't until about 5 or 6 years that I re-entered the field, and came across this article by the Koptia group and work done by Kirill Kovtunov, who was memorialized earlier today by Igor. And I just love this article, and it made a huge impression on me and really inspired me to jump into this field. And I had the good fortune to have some Skype meetings with Kirill, and he visited Gainesville a few years ago together with Edward. And the sad thing is that the tentative plans that we had made to collaborate and work together will not materialize, but certainly his legacy in this field is quite substantial and has had a huge effect on many people. So as Kirill has mentioned earlier, the hydrogenation over metals like nickel, palladium, platinum, rhodium is not efficient in terms of preserving the spin order of singlet hydrogen. In fact, it's inherent to the mechanism of hydrogenation, which is known as the Hori-UT-Polanyi mechanism. It can be broken down into 3 steps where the hydrogens add to the alkene in one at a time. And during that time in between the addition, which is also reversible and can lead to HD exchange between the molecule and the surface. In fact, that's how this mechanism was deduced from the deuterium isotope labeling study. That that together with the fact that the diffusion of hydrogen is extremely rapid with practically no barrier. So the singlet order upon the chemisorption is lost. So it is really true that nobody really expected this class of catalysts to yield a FIP signal, yet they do. It's small, on the order of a few percent typically, depending on the metal and the support. So we characterize the pairwise selectivity. It's kind of a key observable in looking at these catalysts from the measured signal enhancement. And we take the ratio of that with the theoretical maximum signal enhancement, and we get what's called the pairwise selectivity. And that can be thought of as the fraction of the added molecules that are formed by pairwise addition. So now in principle, for two-spin system with using 100% parahydrogen, in Altadena mode experiment, the polarization of 100% is attainable. So there's lots of room for improvement in the pairwise selectivity there. But on the other hand, there are many advantages of this type of catalyst. They're as listed here. They're robust, they're inexpensive, they're scalable, and perhaps most importantly, they generate catalyst-free products. So if we want to address these shortcomings, we really, the solutions to these problems really lies in catalysis science. And so we've been very fortunate to pair up with some of the leading catalyst synthesis groups, as I've mentioned earlier, to try to tackle this problem. Experiments on gases, gaseous substrates like propylene, which we regard as kind of a model alkene substrate with chemically inequivalent adsorption sites. We study those reactions with the apparatus shown here. We use mass flow controllers to mix the reactants, and we dilute them with nitrogen because it's a highly exothermic process. And then under continuous flow condition, we really have an Altadena condition where we go from a strong coupling regime where the reaction occurs in the catalyst bed to weak coupling at high magnetic field. Now, I just want to highlight one result here. It actually came up in an earlier talk today about the metal support interaction. So it's not only the identity and properties of the metal that are important, it's also the support can play an important role. And one of the first things we did here is we actually looked at these metal support interactions, which are well known in the catalyst community. And these interactions are actually reversible, and they can provide signal increase in the pairwise selectivity by an order of magnitude. And they are reversible, so that if you reoxidize the sample. So non-reducible supports, on the other hand, delivered lower pairwise selectivities. But still, we're talking about pairwise selectivities of a few percent here. Lots of room for improvement. So we turn to the bimetallic catalyst, and it's very well known in the catalyst community that bimetallic catalyst can offer increased catalytic performance in terms of selectivity as well as conversion. But there are different types of bimetallic catalyst. You can have an alloy of the two components, which is basically a solid solution with continuously variable proportions, or you can also have a highly ordered stoichiometric compound, which is called an intermetallic. That's the structure here, obviously on the left. So just following or trying to exploit the concept that's so applicable to other reactions, we started to investigate the intermetallic nanoparticles, and the effects can be categorized as two types. There's a geometric effect, because obviously you're changing the spacing of the active metal, but in addition, you can also change there's electronic effect, which can also affect the activation energies for the process. So we have really had the good fortune to team up with Professor Wong's group at Iowa State, and they a few years ago developed a very novel synthesis of these intermetallic compounds. Now, if you just mix two metals together and heat them up in reducing atmosphere, you're going to get particles that are agglomerated. But they figured out that by using an encapsulation shell, by encapsulating platinum seed particles in mesoporous silica, that they could prevent this aggregation of particles, and then under the high temperature treatment that's needed to get the intermetallic phase. And if you want to read more about the synthesis and some very beautiful work by Wenyu's group, you can look at these articles and ACS catalysis and nature catalysis. So now if you look at the TEM, you can really see very clearly that these structures are highly ordered. The crystal structures are very well defined. So on the left, you see a lower resolution TEM, and you can actually see the gray area surrounding the metal core there is the mesopore silica, and this is in this case PT3 tin. And at a higher magnification, you can actually very clearly see these threefold platinum sites that are vertex connected and interrupted by tin atoms, whereas the platinum 111 surface is just contiguous threefold hollow sites. And that's significant because these threefold hollow sites are known from high vacuum surface studies by Cole's group, primarily in the late 90s, to play a very important role in activating dissociation of hydrogen. Okay. The PT tin particles have different crystal structure, but because of the added tin in the structure, it's one-to-one, you no longer have those threefold sites. So we were really fortunate that there existed a large body of this high vacuum surface science literature that we could draw on in the interpretation of and explanation of the catalytic performance in experiments with parahydrogen. So I'll show you one of the consequences of introducing tin. It has what we did in this experiment is we loaded a U-tube with each one of the catalysts, and it's very simple experiment. We flow para-enriched hydrogen through the U-tube, and we look at the extent of the back conversion to orthohydrogen. And we did that by NMR, and you can see that the performance or the three different catalysts have very different behavior in terms of, and very different activity in terms of the back conversion. You can see platinum, even at room temperature, can significantly back convert H2, or parahydrogen. Whereas PT3 tin, you need to increase the temperature. In PT tin, you need to go up to like 200 degrees before you start to see the back conversion. And this is one of the indications that we have that actually hydrogen is not chemisorbing as atomic hydrogen, that it's absorbing onto the surface as molecular hydrogen. In terms of the performance in an Altadena experiment, you can see the reaction with propylene. The pure platinum particles had very high conversion, as you would expect. As you increase the tin, the conversion was not really affected, but you put in one-to-one ratio of platinum to tin, there's almost no conversion at all. And on the other hand, in the experiments of parahydrogen, platinum gives almost no Altadena signal, but the signal increases significantly. In fact, the pairwise selectivity of the hydrogenation increased by 2 orders of magnitude by the incorporation of tin into the structure. And by the time you get to the one-to-one, you're up to 11.7% pairwise selectivity, which is higher than any monometallic nanoparticle catalyst for hydrogenation of propylene. And you see it's actually a 1200-fold enhancement. And to our knowledge, that's a world record in terms of the pairwise selectivity of hydrogenation over a supported metal nanoparticle catalyst. Now, when you look at propyne, where the reaction rate is even faster than propylene, it gives the hydrogen atoms even less time to diffuse away from each other. And for this reaction, this is some recent unpublished work by Yong Du in my research group. You're getting a 17.2% pairwise selectivity, which is now starting to rival, if the experiments were done with pure parahydrogen, you would, in principle, get 17.2% polarization. So you're really seeing enhancements that are rivaling DNP or homogeneous hydrogenation by homogeneous catalysis. And to our knowledge, that's a world record for propyne. So why is it? As I mentioned, these threefold sites play a critical role, and because they are crucial for the low activation energy dissociation of H2. But in addition, once you incorporate tin into the structure, it drastically reduces the diffusion and increases the barrier. The activation energy for diffusion of hydrogen on the surface increased by about an order of magnitude, going from platinum to PT3 tin. and we expect that this diffusion is even slower on PT10, although those calculations are not available. So, as I mentioned, these experiments were done by Dr. Evan Zhao. He's now currently a postdoc with Claire Gray at Cambridge. Just got a Nature paper on completely different research field, looking at in situ measurements on organic battery material. But he did these also demonstrated the possibility to do hydrogenation reactions in solution. So the catalyst is insoluble. You bubble the parahydrogen, it stirs it up into a suspension or a slurry-like state, and you can see significant Pasadena signals or Altadena signals, and he demonstrated both of them. Now, one of the things that Evan did was really, he did a really clever thing and made a very good observation, is that in doing these experiments in water, in methanol, there was an extra signal that appeared that he couldn't explain. And so he did a control experiment, and I'm going to show you what that control experiment was. It's an unbelievably simple experiment. He just took 50 milligrams of the PT3 tin catalyst, put it into an NMR tube containing 99.9% enriched D2O, applied a pressure, hydrogen pressure of about 7 bar, which increases the boiling point of the water to about 160 degrees C. So we could increase the temperature to 120 degrees and we still got liquid water present. And then he just bubbled the parahydrogen through the NMR tube, through the solution. It stirs it up into, like I said, a suspension slurry. He bubbled the parahydrogen, the 50% enriched parahydrogen, for about 30 seconds, and then he very quickly inserted the NMR tube into the NMR spectrometer. And you've seen movies of people doing this throughout this conference. It's very exciting. Unfortunately, I don't have a movie. But so, I mean, this is a control experiment. It shouldn't work. You shouldn't see any signals. There's no substrate here. Right? There's no hydrogenation substrate, just D2O in the catalyst. Just these two ingredients, very simple. Yet when you do, if you do the experiment and transfer the two quickly enough, you can see a very clear emissively phased NMR signal, and that is due to hyperpolarized HDO. And it is properly phased, I can assure you, properly phased spectrum, because if you repeat the experiment with normal hydrogen, you get this tiny little peak down here in the bottom and the lower spectrum. This work came out a couple of years ago now in the journal Chem. So I'd like to tell you also that this experiment, which we call the swamp effect, it stands for surface waters are magnetized from parahydrogen. Because we're here in Florida, it's a very swampy area. And so you can see that this worked for D2O, it works for deuterated methanol, and it works for deuterated ethanol. And interestingly, for these other molecules, for the methanol, you can see the proton impurity of the methyl group also becomes hyperpolarized with emission phase. And on the ethanol, the methylene impurity proton also shows a negative enhancement. But the methyl group doesn't appear to show any signal enhancement. So it turns out that this is a very crucial, this observation of the enhancement on the methyl and methylene groups here turns out to be a very important clue into the mechanism of this swamp effect. And I'm going to tell you a little bit more about that now. So in addition to the hyperpolarization enhancement of the HDO, Evan also reported that with that the HDO signal grows in with the amount of hydrogen that you bubble through the solution. So that's the HDO peak increasing after an induction period. After the first few cycles, it increases linearly with the amount of hydrogen that you bubble to the sample. And that was a pretty clear evidence of exchange between H2 and D2O that's mediated by the catalytic surface. And so naturally, we began to hypothesize that this HD exchange mechanism was responsible for delivering the parahydrogen enhanced polarization that we see in the swamp effect. So, but on the other hand, if you think about it, this would seem to violate one of the basic tenets of the parahydrogen-induced polarization, is that the fundamental requirement of the pairwise addition, right? But in terms of, but also I should mention that Evan further confirmed the HD exchange through the observation of the HD signal. In addition to the growth of the HDO signal, he could also see clear signature of HD formation, which also is very definitively explains, can only be explained by HD exchange process between H2 and D2O. Okay, so that process is actually studied in the literature by the group of Henkelman and Mullins at the University of Texas, Austin, and they, through a combination of high vacuum surface science studies and DFT calculations, were able to propose the mechanism shown here. The important aspect of this is that one of the protons of the adsorbed H2 is oxidized and the electron is taken up by the metal surface. And ultimately there's a formation of a hydronium-like species, and then the electron then is transferred back to a deuteron, and then there's an exchange. So that can explain the net reaction that we are observing. So it all seemed to be falling into place. The only problem is how to explain the polarization transfer for a non-pairwise mechanism. But there is a precedent for that, and I think this work was referenced earlier in the conference by Professor Duckett. He showed this paper, mentioned this paper by Richie Eisenberg, which showed in a hydroformylation reaction that one can have a single hydrogen transfer and still observe parahydrogen enhanced polarization. The key is that the magnetic equivalence is broken in the dihydride form. So there's no violation of the fundamental tenet of the pairwise selectivity, as long as one of the intermediates is formed is magnetically equivalent. Then what happens after that can be a single atom transfer. So we actually proposed a mechanism analogous to 1H, where the hydrogen adsorbs, the parahydrogen adsorbs into chemically inequivalent sites. And then what happens next is the oxidation of one of the hydrogen atoms and attachment to a D2O molecule to form the hydronium-like species and electron transfer of metal. Then there is a migration of the charge on the hydronium-like species, followed by the recombination to form HD and HDO. And we actually proposed a density operator model for this, where the hydrogen, first you have the adsorption of HDO on the surface, the chemisorption of H2 with retaining dipolar coupling into chemically equivalent sites, where the Hamiltonian can be written now here as for the two-spin system as shown here. Since it's a solid, we expect the dipolar interaction. They may be dominant, although the possibility of a J coupling mediated through the metal can't be completely excluded. What happens in terms of the density operator is you have the singlet, then in the under the influence of singlet-triplet mixing, then you write the density matrix by expressing the singlet state in the eigenbasis of the adsorbed phase Hamiltonian. And after kinetic averaging, one can then throw away off-diagonal elements in the density matrix. And if you take the trace with the proton that transferred to the HDO, then you can get up to a -1/4 spin on the A spin. And so, in fact, if you calculate this polarization of the B spin, it's exactly opposite. This model, which depends on the coupling strength in the adsorbed Hamiltonian, it predicts that at zero field or at high field, there will be no effect. And so there's some intermediate field, in fact, where the sine 2 kappa goes to 1. That's where basically the coupling strength is about equal to the chemical shift difference. And in fact, a quick field dependence here demonstrated that simple field dependence demonstrated that the expected behavior is followed. But of course, we submit this paper to Kim, and we had a very astute and excellent reviewer, and I suppose he's out there, and I'd like to thank them for really questioning this hypothesis and making us think about that more deeply. But they were pretty rigorous. They asked us to prove the mechanism. Anybody who's worked in chemistry knows that proving a chemical mechanism, basically you need to disprove all of the other possible or reasonable mechanisms. And so that is something hard to do. So we had to postulate alternative spin exchange mechanism, either through the incoherent process or through a coherent transfer, analogous to the Saber effect that could occur through a level anti-crossing involving 3 spins. So the question is, to try to really determine this mechanism, we have almost no information. We don't know any of the dipolar couplings. We don't know any of the chemical shifts. We don't know the exchange time of water on and off the surface. It's very unlike the situation where all these aspects are very well defined, as you have in a Saber experiment. So, but we could at least rule out the possibility of a 1H mechanism, because the 1H should not depend on the protonation level. But on the other hand, a spin exchange model, you have to have a proton on the target substrate in order to have a spin exchange. And through looking at the effect of the Swamp signal on the extent of the protonation, which increases with the bubbling cycles, you can see that the non-exchangeable proton of the methylene, of the methyl group, in the case of methanol here, is just basically does not change with number of cycles, whereas the Swamp signal of the exchangeable proton does increase. And so that led us to the conclusion that this is a spin exchange mechanism. I just want to, in closing here, just mention a related result. And this was work by one of our, the session chair, I believe, looking at, or one of the organizers, looking at the Saber effect in a water-soluble Saber catalyst. And they saw very intense water hyperpolarization of HDO, as well as hyperpolarization of the HD. And you can see they're oppositely phased in exact agreement with the 1H model. And that is very clearly, and has been also demonstrated in a follow-up paper by the same group, to be a 1H mechanism. Well, finally, I want to give you, I know I'm just about out of time here, our vision for the future is the hyperpolarization of pure HDO using basically, we call it the quantum espresso machine. Pack the reactor bed with PT3 tin, and we pump it up with parahydrogen, and out comes the hyperpolarized water. And since it's a very murky, the quantum mechanics of that process is still very murky, I'm going to put a lightning bolt there, since we don't really know what's going on. But hopefully one day, preparation of hyperpolarized water with the large signal enhancement will be routinely done and can be done conveniently in your local lab. Okay, so I'm gonna finish up here with my conclusions. We find that the PT10 is, INPs give very high pairwise selectivity, higher than monometallic formulations. The PT10 INPs can also polarize biomolecules and polar solvents like water, and give catalyst-free hyperpolarized agents. Furthermore, these PT310 INPs can catalyze what we call a completely new type of FIP effect, which we call swamp. And the mechanism is still unclear. We're working on that in the systematic studies. And big question is, how general is this? And there are other compositions, can other catalyst compositions give similar swamp results or better results? And we do have some work. We do have demonstrated several other compositions, but I'm not quite ready to disclose those results. But hopefully sometime soon you'll see that coming out. Okay, and with that, I'll conclude my presentation, and happy to answer any questions.
All right, thank you very much. That was an awesome talk. We do have a couple of questions. We don't have time for all of them, but I'll just jump right in. First question, what is the conversion of propine over the PTSN catalyst at conditions when the polarization or the conversion or the pairwise addition is 17%?
Yeah, so it's still pretty low, and I think the conversions are on the order of a few percent under these conditions that we ran at. So One thing I didn't mention, in all honesty, I didn't mention anything about conversion. And so that's going to be, for applications, that's going to be essential to get not only high pairwise selectivity, but high conversion. And in some cases here, these record level enhancements are also, we also have very low conversion, some less than 1% in some cases.
Okay, this is a potentially related question. Can you provide details on the TOF, which I hope means turnover frequency, for hydrogenation with 10 platinum particles? How does this compare to published ligand-coated noble metal nanoparticle?
Great question. So recently we just started calculating the TOFs to sort of characterize catalytic rates, but calculating turnover frequency does involves some assumptions that may or may not be good. And in particular, you need to know the contact time of the hydrogen and the substrate on the surface. And that is difficult to estimate. So I think at the time that work was done, we weren't actually reporting the TOFs, although I think it's a good point. We should go back and take a look at that. Good question.
Okay, great. Both Thomas and I also have additional questions that we'll probably bug you about afterwards, but for now we'll go ahead and move on to our next speaker. Thank you very much.
Yeah, thank you.